Hello everybody. I once again have a sick child, so I will not be there today, but here are the notes on our word problems that use logs and exponentials. We're going to be looking at compound interest problems. I apologize, I cannot get this shadow to go away. It's driving me crazy, but that's okay. So we are going to talk about compounding interest today. So let's say you have $100. And there is a bank that is going to give you a certain interest rate on your bank account every year. So let's say this is some kind of a savings account or investment account. And let's say you got really lucky and you had an interest rate of 100%. And if you think back to, so we have $100, I'm going to call that P for principal. And our rate is 100% interest. So if you think back to like when you first learned about percents, we know that 100%, if we change that to a decimal, it will be 1. So we're going to use 1 as our rate here. So let's think about if this rate was calculated once a year. How much money we would earn an interest at the end of that year. So if I have a 100% annual interest rate and it's calculated once a year, then at the end of the year, I should get double my money. I should get 100% of it added in interest. So I'm going to say I start with $100. At the end of the year, I'm going to have 1 plus my interest rate multiplied by the $100. Because 1 would be how much I started with plus however much I'm gaining in interest. So for this problem, I would start with $100, and at the end of the year, I'd have how much I started with plus the 100% in interest, and I would end up with $200, which is great. So I've doubled my money with that 100% interest here if it's calculated just one time at the end of the year. But let's say you found a bank who said, we will divide your interest, your 100% interest rate up and give it to you twice a year. So after 6 months, we'll give you 50% interest. And then after another 6 months, we'll give you another 50%. So let's say it's calculated 2 times a year. So if we want to know how much money we would have at the end of the year, we take our initial investment, which is $100, times 1 plus, remember 1 is because that's how much I started with, plus our new interest rate, which would be the 100% interest rate divided by 2, because they're going to give us half of the interest rate twice a year. Let's see, but they're going to have to do that 2 times. So we're going to say that we're going to square that because it's going to happen twice. So if I go ahead and type this in my calculator, 100 times in parentheses, I'm just going to type it in exactly like it is, 1 plus 0.5 squared, I get $225. So I'm going to earn more in interest if they calculate it twice, because what happens then is that the second half of the year, I have more money that's earning that interest rate. So what if they calculate your interest like, let's say 12 times a year, so once a month. You have your initial investment of $100 times 1 plus our rate, which is 100%, but we're going to divide that up 12 times throughout the year. Okay? And we're going to have to do that 12 times because I'm going to calculate that interest 12 times. So if I type that in my calculator, 100 times 1 plus, just going to do 1 divided by 12, close the parentheses and raise it to the 12. Oh, wow, this time I have $261.30. Okay, let's say you get really, really lucky and you have a bank that says we will do it 365 times. Every day we'll calculate your interest and add it. So calculate it 365 times a year. We'd have 100 times 1 plus 1 over 365 raised to the 365th power. So let's see how much money that would be. So if I take 100 times 1 plus 1 divided by 365 and raise that to the 365, I get 271.40, let's say 46 cents. So 271 and 46 cents. But if you'll notice, like, it appears that I'm sort of reaching a limit here. Like, you know, if I compounded it, so let's say I calculated the interest like 1,000 times. It appears that maybe I'm not going to keep getting infinitely much. That does not make sense. An infinite amount of interest. Like, there's probably going to be this limiting amount where no matter how much I compound it, I may never pass that amount. So let's see if we compound the interest 1,000 times in a year, how much money I would have. So I'm going to do the same thing I just had. I'm changing that 365 to be 1,000. And notice I get something that's really similar. I get 271.69. So it appears that we're reaching some sort of a limit, you know, maybe around $272, somewhere around there, that no matter how much I compound the interest, I'm not going to pass that certain point. So before we get to that idea of compounding the interest infinitely many times, we're going to work some problems out using this formula here that we've kind of been using without writing it down. So the formula for compounding interest is this: A equals P times 1 plus R over N to the NT. And I'll explain what each of those variables means. So P equals your principal which is your starting amount. A is your, that stands for like amount, but that's the amount you end with. So after the interest has been calculated, that's the A. R is your annual interest rate. N is the number of times the interest is compounded each year. And then T is the number of years. Okay, so we're going to work out problems where we're solving for these different variables. You'll be given information about some of them, and then you will have to solve for some of the other parts. Let's see. Okay, so for our first example, let's go to this paper here. Okay, it says you are saving money to buy a car that costs $16,000. If you put $8,000 in an account, earning 12% interest, compounded quarterly, how long will it take to save the money? Okay, so let's kind of identify each of our variables. Remember, our equation is A equals P times 1 plus R over N to the NT. Okay, so the car costs $16,000, so that's how much we want to end up with. So that's going to be our A. The $8,000 is how much I started with, so that's the P. The interest rate is 12%, so for R, I'm going to use 0.12, so you always want to change it to the decimal version. It's compounded quarterly, and what that means is 4 times a year. So we're going to use 4 for the N. And it says, how long will it take? So the T value, that's what I don't know. That's what I'm actually going to be solving for. Okay, so I'm going to plug in all these values to the equation. So I have 16,000 equals 8,000 times 1 plus 0.12 over 4 to the 4t. And that t right there is what I'm solving for. So I'm solving for actually a variable that's in the exponent. So I need to get this t by itself. And these will all be calculator problems. So first thing I'm going to do is divide by 8,000. And I have 2 equals 1 plus, let's see, 0.12 divided by 4 would be like 0.03. I'll just write that to make it a little bit more simple. Okay, so anytime you are solving for a variable that's in the exponent, the only way to get this variable out of an exponent is with logs, with rules of logs. So whenever we're solving an equation, we can do anything we want to it as long as we do it to both sides. So I'm going to actually just natural log both sides. And what that then allows me to do is use the rules of logs to move this 4t to the front. Remember the power rule of exponents? So that's why we log both sides, so that we can then move that 4t to the front. So I have natural log 2 equals 4t times the natural log of, that'd be like 1.03. And then to get the t by itself, the last thing we need to do is just divide both sides by 4 natural log 1.03. So that kind of cancels out the 4 and the natural log, leaving only the t. So in my calculator, I'm going to type in natural log 2 divided by 4 natural log 1.03. And whoops, you've got to put parentheses around your denominator or else it won't divide by that whole thing. And I got 5.86. Okay, so do you guys see that? So natural log 2 divided by 4 natural log 1.03. So t equals 5.862, and that would be in years. So the time, the t variable for all of these will be in years. So actually that's pretty good, doubling your money in less than 6 years. And to get a 12% interest rate, you have to be invested in like a good stock or mutual fund or something. You're not going to get that interest rate at a bank. That will be from an investment account. Just FYI. Okay, so that's kind of using this formula. And so most of the time actually on the worksheet, you're going to be just solving for A, which is pretty easy because it's already by itself. So you'll just plug in everything, type in your calculator, and you get A. But if you're ever solving for the exponent, that's where you have to log both sides. And it actually doesn't matter if you use natural log or common log, you'll get the same answer. So on the worksheet, they'll say things like the interest is compounded quarterly, so that would be 4 times a year. Compounded monthly would be 12 times in a year. Compounded yearly, so that would just be 1 time a year. Daily would be 365 times. Yes, so I believe those are the only words they use, but your end value, remember, is always the number of times in a year that the interest is compounded. So earlier, when we kind of talked about how compounding interest different numbers of times in a year could affect the amount you would have at the end of your investment, we kind of saw that at a certain point, you're going to stop seeing a huge increase in the amount of money that you make from compounding it more times. So just going back to what we started with, we saw if we just did it once at the end of the year, we would double our money with 100% interest rate. If we did it twice, we'd actually end up with $225. If we did it once a month, we'd end up with $261. If we did it every day, we'd have $271.46. And then if we did it 1,000 times, which is almost 3 times as many times as daily, we would only gain like another 20 cents. So at some point here, you're going to reach that limit. And so even if you were compounding the interest infinitely many times, so we call that continuously compounding, it's always calculating your interest. That's actually something that we can calculate because we're approaching this limiting value. And that's where E comes into play. So that is the usefulness of E, is it allows us to calculate continuously compounding interest. So E is really important whenever we're doing exponential growth and things like that. And it has other applications that really are easier to explain if you know calculus. So we're going to kind of leave it at that E is used for continuously compounding interest. And you'll notice that this value that I was approaching, this 271.69, remember I told you, let's see, E from my calculator, it equals 2.71828. So that is not an accident that these two things are very, very similar. So you can see that E is involved, right? Because our E value is like, you know, this divided by 100, because here I did $100, but if I had just done $1, then I would be approaching this value, which is E. So notice I'm getting closer and closer to this 271.82. So this would be the max amount of money you could get. We're really close here, compounding 1,000 times. Okay, so the equation for continuously compounding interest, so our second formula of the day, continuously compounding, is this. A equals P E to the RT. So a lot of times people call us PERT because obviously it spells PERT, so that's kind of how you can remember it. The variables mean all of the same things. So A is still the amount at the end, P is the amount at the beginning, R is your annual interest rate, and T is the number of years that you are going to be investing. So let's do a couple of examples with a PERT, and then we'll be done for the day. So both of these formulas, the PERT formula and then our just compounding for different times a year, this one, both of those will need to be memorized for the test. Okay, so if $200 is invested at a 6% annual interest rate, and compounded continuously, when will the investment be worth $300? Okay, so if $200 is invested at 6% annual interest, compounded continuously, when will the investment be worth $300? So to set this up, our A value, so the amount we end up with, will be 300. Our P value will be 200. That's the amount we start with. Our interest rate, 6%, so we would put 0.06. And our t-value, we don't know that. That's what we want to know. So setting this up, I have 300 equals 200 times e to the 0.06t. So we're going to divide both sides by 200 first. So I get 3 over 2 equals e to the 0.06t. Now, just like the last one, our variable is in our exponent. And anytime we want to get a variable out of the exponent, we need to use logs. So I'm going to natural log both sides here because I can do anything to an equation as long as I do it to both sides. And remember, that is going to allow me to move this 0.06t out to the front of the log and out of the exponent. So I have natural log of 3/2 equals 0.06t times natural log e. But what's the natural log of e equal? It equals 1. So that actually goes away. So it's actually really nice when we do the continuously compounding problems because of the e. When we natural log both sides, we get rid of that e. So the only thing I have left to do is just divide both sides by 0.06. And I can type that in my calculator to solve for t. So in the calculator, I'm just going to type in, oops, clear, natural log 3 over 2, so sorry, natural log 3 over 2 divided by 0.06. Okay, and I get t equals 6.758 years. Okay. All right, let's just try one more, and then you can work on your worksheet. This is the last thing that we're learning with exponents and logs are these interest problems, word problems. And then tomorrow we're going to be reviewing, and Monday we will be testing. So just keep that in mind. So example 3 says a bank promises to double your money in 6 years. That'd be pretty nice. What is the interest rate if it is compounded continuously? Okay, what's the interest rate if it's compounded continuously? So remember our equation, A equals P times e to the RT. So it's the PERT equation. It says they promise to double your money. So it doesn't actually tell you what the principal and the final amount would be. So you can actually put in anything you want. Just make sure you double it for your final amount. So you could put in $1 and double it to $2. You could put in 1,000, double it to 2,000. And it turns out it doesn't matter which amount you start with and then double it, you'll get the same answer here. So I'm just going to use 1 and 2 because that's kind of the most simple way to do it. So I'm starting with $1, I'm going to double it to $2. So I have 2 equals 1 times e to the r. So I'm solving for r. What's the interest rate? And the time here is 6 years. So I have 2 equals 1 times e to the 6r basically. So you could divide both sides by the 1, or, you know, that's kind of pointless. So here's what I get. I'm going to natural log both sides. I remember doing that allows me to move this 6r out of the exponent. But remember the natural log e part, that will always go away. So I didn't even really need to write it. I just kind of wanted to show you that one more time. So we move the 6r to the front. You just have natural log e, which equals 1. So that goes away. So I divide both sides by 6. And in my calculator, then I'm just going to type in natural log 2 divided by 6. So I get 0.1155. So I have R equals 0.1155. But I want to give it as a percent since it's an interest rate. So I'm going to say that's 11.55%. So if you can find someone to guarantee you an 11.55% interest rate, you would double your money in 6 years, which, like I said earlier, the only place you're going to find that is if you get lucky and find a good stock. Alrighty, so your worksheet looks like this. So one side is continuously compounding, where you'll be using the PERT equation, solving for different parts of the equation. Here at the bottom, numbers 7 and 8 deals with bacteria growth. So that also is modeled exponentially with the same equation, basically. So for 7 and 8, the only thing different is that you're using different variables. So the formula here is y equals NE to the KT, but it works the exact same way. So N is the number you start with, the Y would be the number you end with, and the 2 hours, we'll use that for our time, and it says find the constant K. So if you know all those variables, then you should be able to set this up. So it's like 5,000 equals 400 e to the K times 2. So it works the exact same way. For some reason with bacteria growth, they just use different variables. So you'll do that same thing, that same equation right here on numbers 7 and 8. And then on the back, it is the compounding interest, different numbers of times in the year. So like the first one, you receive $100. She's saving it with 5% interest, compounded quarterly. So that's where you do the 0.05 over 4. How much money will she have by her 16th birthday? So if she's 13, she's going to 16. That's 3 years away. So I'm using this formula here on the back. And that's it. If you finish it before class is out, you can turn it in. If not, it will be due first thing Friday morning, and then we're going to start reviewing for your test. So good luck. Thanks for watching, and have a good day. Bye.